Section 5.6 is Exponential and Logarithmic Equations. With exponents and logs, there are some rules that you need to memorize, like the product rule, the quotient rule, the power rule for both exponents and logs. Those need to be committed to memory. So this is one math test that you can actually make a note card of things to study. Also, the definition of logs is going to be used quite a bit. We use that to rewrite logs as exponents and exponents as logs. Just to refresh your memory, let me write down the definition of logs that we're going to be using. The definition of logs says that y is equal to log base a of x if and only if a to the y is equal to x. This definition of logs we use to rewrite logarithmic equations as exponents and vice versa. We're going to be using this as we solve equations. Remember, if you watch the video, I'm not sure if Mr. Duncan pointed this out when he was lecturing, but logs are inverses of exponents. Remember how we get an inverse function from a function? We switch x and y. If you look at this exponential expression, you see how the x and the y have traded places, because normally we would write y equals a base raised to a power of x. For example, y equals 2 to the x. Well, because x and y are switched in the exponential form, that means that logs are actually inverses of exponential equations. That's an important point to make. If you have not watched the videos over Chapter 5, the previous videos that I did, I strongly recommend you do so before you get too deep into the homework or even attempt the review that I have posted, because there's a lot of things that I point out in those videos that you need to understand, and I've pared them down so that they're not terribly long. I don't think any of them are much over 20 minutes, if that. Alright, an exponential equation. An equation in which one or more variables occurs in the exponent of the expression is called an exponential equation. We use the power rule of logarithms to rewrite this log. Remember, the power rule says that if you have log base a of something raised to a power, you can take that power out of the argument and move it in front of the log. We use this rule to get variables out of the exponent. In example 1, we're going to be solving these three equations, and we're going to be using this power rule for logs in order to do this. In part A, the variable is in the exponent, but we can't take the log of both sides of the equation until we have this exponential expression by itself. So your first step is going to be to isolate the term with the variable in it. Remember, in algebra, we can do pretty much anything we want to an equation as long as we do the same thing to both sides of the equation. So in order to get this term by itself, I need to subtract 1 from both sides of the equation. And when I do that, I get 5 times 1.2 raised to a power of x equals 25. This term is still not considered isolated until the 5 is divided off. So that's my next step, is to divide both sides by 5. When I divide the 5 off here, I'm left with 1.2 raised to a power of x equals 5, because 25 divided by 5 is 5. Now is where I use this power rule. And I want to use a log that I have a button for on my calculator so I can get a decimal approximation if I ask you for a decimal approximation. So I'm going to choose to use the natural log. I'm going to take the natural log of both sides of the equation. So you see, now I can use this power rule right here to bring that variable out of the exponent. And when I rewrite this, I get x times the natural log of 1.2 equals the natural log of 5. Remember, natural log is a mathematical operation just like square root is a mathematical operation. Our minds tend to want to reject the concept that that's a mathematical expression because it doesn't look like the symbols that we're used to seeing for mathematics. But natural log is a mathematical operation just like the square root is a mathematical operation. Now, square roots don't mean anything unless I put something underneath the radical. Natural logs don't mean anything unless I have an argument for the natural log. So these are a variety of mathematical operations. When we solve an equation, the goal is to get the variable by itself. If there's no symbol in between these two terms, the assumed operation is multiplication, and division undoes multiplication, so I'm going to divide both sides by the natural log of 1.2. And that will give me my final answer of x equals the natural log of 5 divided by the natural log of 1.2. And this is what I would consider to be my exact answer. If I ask you for a decimal approximation rounded to, let's say, 3 or 4 decimal places, we would have to go to our calculator. And on our calculator, to get a decimal approximation for this, we would hit the natural log of 5. Make sure you close the parentheses on your calculator, because your calculator will automatically open parentheses after you hit ln. And then we're going to divide that by the natural log of 1.2 and close the parentheses again. And when we do that, we get this is approximately equal to 8.827. Notice whenever I use a decimal approximation, I put the wavy equal signs. That's the symbol that we use for approximately equal to. Alright, in part B we have 1/4 raised to a power of x minus 1 equals 1/9. Notice the variable is in the exponent. How do I get a variable out of an exponent whenever I have an equation to solve? I use the power rule for logs. And what you do to one side of the equation, you have to do to the other. So I'm going to take this side of the equation and set it equal to the natural log of the other side of the equation. So that's going to give me the natural log of 1/4 raised to a power of x minus 1 equals the natural log of 1/9. Now I can use my power rule. The power rule says that this exponent, x minus 1, comes down out of the exponent and I multiply it by the natural log of 1/4. Notice I put the x minus 1 in parentheses. I did that because this is x minus 1 times this quantity, the natural log of 1/4. Anytime you have a constant outside of parentheses, you need to distribute that constant. So this is going to give us x times the natural log of 1/4 minus 1 times the natural log of 1/4 equals the natural log of 1/9. The goal when you're solving an equation is to get the variable by itself. So this is a constant term that I can move by adding that term to both sides of the equation. So I'm going to add the natural log of 1/4 to both sides of the equation. When I do that, these terms are going to cancel out because I'm adding and subtracting the same thing, and that's going to leave me x times the natural log of 1/4 equals the natural log of what? Can I add the 1/9 to the 1/4? No, we don't have a rule that says that you can add the arguments together. So I write both of these terms down, the natural log of 1/9 plus the natural log of 1/4. Now to get the x by itself, I divide both sides by the natural log of 1/4, and that gives me my final answer of x equals the natural log of 1/9 plus the natural log of 1/4 divided by the natural log of 1/4. That's a good question. The question was, will these natural logs cancel out? Can we cancel or reduce a fraction if you have addition between terms in the numerator and denominator? No, I can't. So it doesn't cancel out. But I do want you to recall the product rule for logs. It says if you have the natural log of x times y, that's equal to the natural log of x plus the natural log of y. This is the product rule for logs. See how I have that plus right there? What I can do is I can multiply those arguments together, and that will allow me to rewrite this as the natural log of 1/9 times 1/4 is 1/36. Divided by the natural log of 1/4. We also have a quotient rule for logs. The quotient rule says if you have the natural log of a quotient x divided by y, you can separate that using subtraction, the natural log of x minus the natural log of y. Notice this quotient is in the argument, not between the logs, so don't make a careless mistake and divide these arguments here. This actually is your exact answer, as simplified as you can get it. If I asked you for a decimal approximation, you could find that decimal approximation by on your calculator doing the natural log of 1 divided by 36 divided by the natural log of 1/4. And just to show you that these two answers are equivalent, I'm also going to type in the first one that I got where I had the plus in between. Because I have a sum in the numerator, I need to make sure that I put the numerator in parentheses. So I have the natural log of 1/9 plus the natural log of 1/4. Close the parentheses for the numerator. Also notice I've closed the parentheses for each of my arguments. Now this entire numerator I'm going to divide by the natural log of 1/4. And notice I get the exact same decimal values. That verifies that these two expressions are mathematically equivalent because I got the same decimal value when I did them on the calculator. So if I asked you to round this answer to 3 decimal places, you would tell me this is approximately equal to 2.585. On part C, we're asked to solve the equation 5 raised to the x minus 3 equals e raised to the 2x. What I want you to notice about this is that your variable is in the exponent. How do we get variables out of the exponent? What do I have to do to both sides of the equation? How do I put them in front? I can't put them in front until I have the natural log. The rule that I'm using to do this is called the power rule for logs. By the way, these rules I'm erasing after I write them down, so you might want to write them in your notes. These are the things that you need to have memorized. The power rule for log says that if you have the log of x raised to a power of n, you can rewrite that as n times the natural log of x. You just take whatever the exponent is on the argument of the log and move it down front. So in order to get these variables down out of the exponent, I have to take the natural log of both sides of the equation. What you do to one side of the equation, you have to do to the other. So I'm taking the natural log of 5 raised to the x minus 3 and I'm setting it equal to the natural log of e raised to the 2x. Now I can move my exponent down front. So I have a binomial expression, so I put my exponent in parentheses so that I remember to distribute that natural log 5. And what is the natural log of e raised to the 2x? It's just 2x. ln, remember, is a log base e, and this is a power base e, and if you compose two inverse functions, they cancel each other out and you're just left with the exponent, 2x. This is called the inverse property of logs. Do y'all remember that? Have you watched that video yet? The inverse property says if you have a log base a of a raised to a power of x, that's going to be equal to x. And if you have a raised to a log base a of x, that's going to be equal to x as well. And we're going to use this inverse property quite a bit. So you need to have this committed to memory as well. Notice if the base of the log is the same as the base of the exponent, you get out whatever you put into that exponent. If the base of the exponent is the same as the base of the log that is inside the exponent, you get out whatever you put into that log. ln is a log base e, that's why the ln's and the e's cancel each other out here. Now we need to distribute this natural log 5 across the parentheses, and that's going to give us x natural log 5 minus 3 natural log 5 equals 2x. I have two terms with an x in them. So I want to take everything with an x and put it on one side of the equation and everything without an x and put it on the other side of the equation. Because I don't like negatives very much, I'm going to add 3 natural log 5 to both sides and subtract 2x from both sides. So I'm going to add 3 natural log 5 to both sides of the equation, and I'm also going to subtract 2x from both sides of the equation. These are not like terms. I can't combine them, so I'm going to just write them both down. I get x natural log 5 minus 2x equals 3 natural log 5 because these terms zeroed out and these terms zeroed out. Now I notice that I have an x in both of these terms, so I can factor that common factor of x out and I'm left with the natural log of 5 minus 2 equals 3 natural log 5. And in order to get the x by itself, I just divide both sides by these constants, natural log 5 minus 2. So my final answer here is going to be x equals 3 natural log 5 divided by the natural log of 5 minus 2. And my decimal approximation I would get using my calculator. And in my calculator I would type 3 natural log 5, close the parentheses, divided by, and now I have a difference in the denominator, so I want to put my denominator in parentheses, and I'm going to type in natural log 5, close the parentheses for the argument on the log, and then hit minus 2, and that will give me my decimal approximation of negative 12.362. So here's your exact answer, and here's the decimal approximation. Know the difference between the two and know how to find both. The exact answer will have natural logs or common logs in them. The decimal approximation won't. Alright, some more problems to practice. You can never get enough practice. So for part A, we have 9 raised to the 2x equals 9 raised to the 4 minus x. What do you notice about these two exponential expressions that are equal to each other? They have the same base. Well, exponents and logs are 1 to 1. That means that if the x's are equal, the y's are equal. Well, if the bases are equal, guess what else has to be equal? The exponents have to be equal. So in order to solve this, all I need to solve is 2x equals 4 minus x. Now this is just a simple linear equation that you guys can solve, but you've got to recognize that you can turn this into this using that 1 to 1 property of exponents. So in order to solve this equation, I'm going to add an x to both sides, and that gives me 3x is equal to 4, and then I divide both sides by 3, and I end up with x equals 4/3. I want to show you that you can check your answer using your calculator. So what I would do is I would take 9, raise it to a power of 2 times 4/3, and that gives me a decimal approximation. Then I would take 9 and raise it to a power of 4 minus 4/3, and that gives me the exact same decimal value. So I did find the right answer for x. X is equal to 4/3 would be my final answer. For part B, I have 6 times the exponential expression 1.3 raised to a power of x minus 4 equals 20. What do I have to do first in order to solve this equation? I have to get this exponent by itself. So what do I do to get this exponent by itself? Add 4 to both sides. And when I add 4 to both sides, I get 6 times 1.3 raised to the x equals 24. Is this considered isolated now, or is there something else I can do? I can divide both sides by 6, and when I divide both sides by 6, I end up with 1.3 raised to a power of x equals 4. How do I get the variable out of the exponent now? Take the natural log of both sides of the equation. So I have the natural log of 1.3 raised to the x equals the natural log of 4. What do I do with the variable now? Put it in front. So that gives me x natural log 1.3 equals natural log 4. And how do I solve for x? What do I need to do? Divide it off of both sides. I divide both sides by the natural log of 1.3. So my exact answer will be x equals the natural log of 4 divided by the natural log of 1.3. And I'm going to be happy with the exact answer for now. I've shown you how to use the calculator already. On part C, I notice that I have an exponential expression that's by itself. How do I get the variable out of the exponent now? Right, I take the natural log of both sides of the equation so that I can use the power rule to get the variable out of the exponent. So I'm looking at the natural log of 1/2 raised to the 1 minus x equals the natural log of 1/7. Now I can bring that 1 minus x out of the exponent, but make sure you put that in parentheses. The most common mistake that I see is students forget to put that exponent in parentheses when there's more than one term there, and then they forget to distribute, which happens to be our next step. We distribute this natural log of 1/2 across the parentheses. And when we distribute, we get 1 times the natural log of 1/2, which is just the natural log of 1/2, minus x times the natural log of 1/2 equals the natural log of 1/7. I want to get the x by itself, so I need to move this term over. And I do that by using subtraction. So I'm going to subtract the natural log of 1/2 from both sides of the equation, remembering that what you do to one side you have to do to the other. And that leaves me a negative x natural log of 1/2 equals the natural log of 1/7 minus the natural log of 1/2. Now what? Divide both sides by a negative natural log 1/2. And I get my final answer of x equals, now this negative in the denominator could be distributed to the numerator, couldn't it? And if I do that, it'll just switch the order of the subtraction. So I'm going to write that as the natural log of 1/2 minus the natural log of 1/7 divided by a positive natural log of 1/2. I would accept this as a final answer unless it was a multiple choice test and that wasn't one of the choices. What rule could I use to combine these two natural logs? Not product. Quotient rule. Because there's subtraction between the logs, we use the quotient rule. So that'll be equal to, let's just look at this as an aside. If I have 1/2 divided by 1/7, you have a fraction over a fraction. How do you simplify that? That's 1/2 times what? And that gives us 7/2. So I could rewrite this as the natural log of 7/2 divided by the natural log of 1/2, using the quotient rule to combine these two terms. The question was, what happened to this negative? That negative got distributed across the numerator, because if you have a over negative b, isn't that the same thing as negative a over b? Well, what I had was that negative in the denominator. If I put that negative in the numerator instead, I could distribute that negative across the numerator, which makes this a negative natural log of 1/7. And a negative times a negative is a positive natural log of 1/2. So that's the mechanics behind how I went from here to here. When I moved that negative up into the numerator, it just switched the order of subtraction between these two terms. Part D, we have 4 raised to the 3x equals 3 raised to the x minus 2. I notice my variable's in the exponent. How do I get the variable out of the exponent? Take the natural log of both sides of the equation. Keep in mind, I could use the common log. It's just that because I teach calculus, we use natural logs all the time. We don't use the common log that much because ln's and e's cancel each other out, and we have a lot of e's in calculus, so we like using the natural log. So that's my go-to. But the same thing would work with the common log. Now I rewrite this as 3x times the natural log of 4 equals x minus 2 times the natural log of 3. What's my next step going to be? Distribute. We're going to distribute that constant of natural log 3 across the parentheses. And when I do that, I get 3x natural log 4 equals x natural log 3 minus 2 natural log 3. I have two x's in the problem, one on one side and one on the other. How do I resolve that? So let's subtract this x natural log 3 from both sides of the equation. When I subtract this, do I get 2x natural log 1? No, these are not like terms because the arguments are not the same. Just like you can't add the square root of 2 to the square root of 3 because what's under the radical is not the same. On logs, if the arguments are not the same, you can't change those arguments. So I just write down 3x natural log 4 minus x natural log 3 equals negative 2 natural log 3 because these terms canceled each other out. Now I have a common factor of x on both sides that I can factor out, and that's going to give me x times 3 natural log 4 minus natural log 3 equals negative 2 natural log 3. How do I get the x by itself? Division. I'm going to divide off that 3 natural log 4 minus natural log 3 from both sides of the equation. What you do to one side, you have to do to the other. So that gives us x is equal to negative 2 natural log 3 divided by 3 natural log 4 minus natural log 3. This I would accept as your final answer, unless it's multiple choice and that's not one of the choices. You need to recognize that that negative 2 could go up in the exponent, and that would give us the natural log of, what is 3 raised to the negative 2 power? 1/9. 4 to the third is 64 divided by 3. That 3 came from the quotient rule here between the logs. The 64 came from the power rule. 4 raised to the third power is 64. If it were a multiple choice test, this is probably how your answer would be written. Alright, logarithmic equations contain logs. To solve a logarithmic equation, we use the inverse property. Here it is again. If you have the base of the exponent and the base of the log are the same, then the bases of the exponent and the log are going to cancel each other out, and you're just left with x. In example 3, we have an equation to solve. The log has to be isolated now, just like we isolated the exponent. In order to get this log by itself, I need to divide both sides by 3. When I do that, I get log base 3 of x equals 4. If you want to solve for x, use the definition of logs to rewrite that log as an exponent. If there's only one log in the equation, rewrite it as an exponent using the definition of logs. Here's the definition of logs. Notice the base of the log is the same as the base of the exponent. What the log is equal to is the exponent, and the argument of the exponent stands alone. So how would I rewrite this as an equivalent exponential expression? 3 to the fourth equals x. And that means that x then will be equal to 81 because 3 to the fourth is 81. On example 4, we have log of 2x plus 1 equals 2. There's no base on this log, so what kind of log is it? It's a log base 10, also called the common log. If you need to see the base, then write it in. How would I rewrite this log as an equivalent exponential expression then? The base of the log is the same as the base of the exponent. What the log is equal to is the exponent, and the argument stands alone. So what is 10 squared? How do I get that x by itself? What do I need to do? Subtract 1 from both sides, and that gives us 99 is equal to 2x. Now what? Divide both sides by 2, and I end up with x equals 99 halves. If you have two logs in your equation, you need to get them on the same side of the equation. Then you rewrite that as a single log using either the product rule or the quotient rule. So that means that I need to move this log to the other side, and I'm going to add log base 2 of x to both sides of the equation. So can I rewrite this as log base 2 of 5x? They have the same base, but they don't have the same argument. So you can't combine them, you just write them both down. So I have log base 2 of 4x plus log base 2 of x equals 2. Now I can rewrite this as a single log using the product rule. The product rule says that if you have a sum of two logs with the same base, you multiply the arguments together. Now there's only one log in the equation, just like what we had in part A. And how did I tell you to solve the one in part A? Rewrite that log as an equivalent exponent. So this would be the base of the log is the base of the exponent. What the log is equal to is the exponent, and 4x times x is 4x squared. So that means that 4 is equal to 4x squared, and in order to solve this, I would divide both sides by 4, and that will give me x squared is equal to 1. How do I solve this quadratic equation? I take the square root of both sides, but when you take the square root of a variable squared, you have to remember plus or minus. So I end up with x equals 1 or negative 1. But can you take the log of a negative number? You can't, and because x was in the argument of the log in the original problem, that means that I don't get to keep this answer. I just get x equals 1 as my final answer, because the negative 1 is not in the domain of this problem. On part C, I don't want that 2 out front so that I can have a log equal to a log. Where does that 2 going to end up? Where does it go? Think about the power rule. We're going to use it in reverse now. I'm not bringing an exponent down front. I'm taking a number out front and I put it in the exponent. So I rewrite this as the natural log of x plus 1 squared equals the natural log of 1 minus 2x. Now I have a natural log equal to a natural log, and because logs are 1 to 1, that means that if the bases are the same, the arguments also have to be the same. So I can solve this quadratic equation x plus 1 squared, which is just x plus 1 times x plus 1, equals 1 minus 2x. So I need to FOIL this out, and I get x squared plus 2x plus 1 equals 1 minus 2x. This is a quadratic equation. How do we solve quadratic equations? We set them equal to what? 0, and then we factor, hopefully. So I'm going to subtract 1 and add 2x to both sides. Add 2x, subtract 1. When I do that, I get x squared plus 4x equals 0. Will this factor? Sure it will. That means that x is going to be equal to what? I get x equals 0 and x equals negative 4. Now with logarithmic equations, because the domain goes from 0 to infinity, not including 0, I have to check my answers. So I go back to the original problem, and if I plug in a 0 for x, I get the natural log of 1. Can I take the natural log of 1? Yes. So that's okay. And when I plug in a 0 for x, I get the natural log of 1. Is that okay? Yes, it is. So 0 is a good answer. X can be equal to 0. The argument of the log cannot be equal to 0. Now I'm going to check negative 4. When I plug in a negative 4 in place of x, I get the natural log of negative 3. Can I take the natural log of negative 3? No, I can't. Even though this is squared, it's not going to work. So this is not going to be an answer. Whenever you're solving an equation involving logs, make sure you check your answers to see if your answers are in the domain of the problem, that they don't make the argument of the log 0 or negative. In the last example, on part A, I have a log in the equation, just one log. How did I tell you we solved that equation? What do I need to do to solve for x, to get the x out of the argument? We rewrite the log as an exponent. So this will be 2 raised to the third equals 4x minus 2. 2 raised to the third is 8. Now I need to solve for x, so I add 2 to both sides. And that gives me 4x equals 10. And then when I divide both sides by 4, I need to reduce the fraction, and I end up with x equals 5 halves. On part B, I have log of 20x equals 5 minus log x. What's the base of this log? It's 10. So I need to get the logs on the same side and the x's on the same side, so I'm going to add log x to both sides of the equation. What you do to one side, you have to do to the other. So on the left-hand side, can I rewrite this as log 21x and add 20x to x? The only way to change an argument on the logs is to use one of the rules that we know with logs, like the product rule, the quotient rule, or the power rule. So these are not like terms because the arguments are not the same. So I have to rewrite this as log 20x plus log x equals 5. Now I can use the product rule because I have addition between the logs. And when I use the product rule, I can rewrite this as log 20x times x equals 5. What's 20x times x? 20x squared. Now I only have one log in the exponent, so how do I solve it? How do I get the x by itself? We change it to an exponent, so the base of my exponent is going to be 10, and I have 10 to the 5th equals 20x squared. 10 to the 5th is 100,000. How do I get the x squared by itself? Divide both sides by 20, and 100,000 divided by 20 is, so I end up with x equals plus or minus the square root of 5,000, but I'm only going to keep the positive one because in my original problem I had an x right here and I can't have a negative value, so I'm going to just keep the positive one. Normally we would do plus or minus, but when you go back to the original problem you can't have a negative number in your argument. So my final answer here would be x equals the square root of 5,000. Now we could simplify this because I could rewrite 5,000 as, well, that's 50 times 100, and 100 is a perfect squared, and 50 I could write as 25 times 2, and 25 is a perfect square. So this would be equal to 10 times 5 is 50 square roots of 2. And then on part C, we have the natural log of x plus 1 equals 2 times the natural log of x minus 1. What do I need to do so that I can solve this problem? Put the 2 up in the exponent, so I get the natural log of x plus 1 equals the natural log of x minus 1 squared. Because the bases are the same, I could rewrite this as x plus 1 equals x minus 1 times x minus 1, because when you square something you multiply it by itself. So that gives us x plus 1 equals x squared minus 2x plus 1. This is a quadratic equation, so I need to set it equal to 0, so I'm going to subtract an x from both sides and subtract 1. And when I do that, I get x squared minus 3x equals 0. This will factor because I have a common factor of x that I can pull out, and I get x times x minus 3 equals 0. That means that either x is equal to 0 or x is equal to 3. And if I go back to my original problem, if I plug in a 0 here, I end up with natural log of 1. If I plug in a 0 here, I get a negative 1, but when I rewrite this with that exponent there, this works. The 0 works. So I'm going to say that my answer is going to be x equals 0 and x equals 3, because the power rule allows me to put that number in the exponent, and that's going to make this a workable problem. If that 2 wasn't there, I could not keep the 0 in my final answer. And this wraps up section 5.6.